Welcome back to Math 332. In this video, we are going to look at section 4.6 in the book, which is change of basis. We are going to make two videos. In the first video, we are going to look at the theoretical construct on how to form the transition matrix. And the second video will be computational. We're going to look at the problems that we saw in class again. We are going to suggest how to make that computational slightly more efficient so that we don't have to do a lot of unnecessary computations. Okay, so this is what we're going to do in this two video. So let's get started. Suppose you have a vector space V, and for simplicity, let's just assume that this vector space has dimension 2. And assume that there are two different bases, B and B prime. As we know, for a vector space, you can have multiple different bases. But since we assume that our vector space has dimension 2, then all these bases should contain only two vectors. It's called U1 and U2 for basis B, and U1 prime and U2 prime for basis B prime. Let me say that again, the vectors U1, U2 could be anything. It could be like column vectors, it could be matrices, it could be functions, it could be polynomial, depending on what your vector space V is. Same thing here for B prime. Regardless of what exactly is your U1 and U2, are they matrices, are they functions, are they polynomial, regardless of all that, the coordinates of vector U1 relative to the basis B prime is definitely going to be a pair of numbers. Okay, in this case, A, B in R2, right? These are real numbers, these are real numbers. Okay, regardless of what is your vectors U2, the coordinates, okay, this is the notation for the coordinates. So the coordinates for vectors U2 relative to basis B prime is definitely going to be a pair of numbers which we call C and D. So this thing is actually an element in R2. So by the definitions of coordinates, if you write your U coordinates of U1 with respect to B prime like this, and U2 with respect to B prime like this, then the vectors, this is the vectors. The vectors U1 is written as A multiply U1 prime plus B U2 prime. U1 prime, U2 prime are coming from the basis B prime. Okay, same thing here for your U2. So A, B, C, D, these are numbers. Okay. So U1, that's the vectors. U1, okay, with this open bracket, and then this subscript B prime, these are coordinates. Okay, so do not confuse which one is the vectors and which one is the coordinates. So if you have these assumptions, these are the coordinates, okay, then you will have this, right? This is the definitions of what coordinates actually means. Okay, so once we have all this, let's assume that we have another vectors V from vector space V. This time, this vector V will have coordinates K1, K2, right? So this is the coordinate. Okay, so this is an element in R2. Again, what this thing means is that your vector V, this is a vector, can be written as a number K1 multiply vectors U1 plus numbers K2 multiply vector U2. And from our assumptions, our U1, okay, from right here, right, your U1 can be written as A U1 prime plus B U2 prime, and your U2 can be written as C U1 prime plus D U2 prime. So K1A, these are numbers, K2C, these are numbers. In fact, they are the coefficients of the vectors U1 prime, so you can factor this thing out, and you can also factor the coefficient for U2 prime. So you will have these numbers multiply these vectors plus these numbers multiply these vectors. Now these vectors are the vectors from the basis B prime. So if you can write V as a linear combinations of these two vectors in basis B prime, then these numbers and these numbers are taken as the coordinates of V, okay, relative to basis B prime. So if you can write things like the things V, the vectors V, you can write in this particular expressions, then immediately the coordinates of vector V relative to basis B primes is this. Okay, so these are numbers K1A plus K2C. These are numbers K1B plus K2D. So instead of write your V, okay, the coordinate of V relative to B prime like this, you can also write in a matrix form, which is this right here. Okay, so this is A K1 plus C K2, B K1 plus D K2. So you can write it like this. And recall that our K1, K2, from the very beginning, our K1, K2 is actually the coordinate of V relative to basis B. So which means that we found a relationship between the coordinates of V relative to B prime and the coordinate for V relative to B. It's the same V here, it's just different coordinates. Okay, so this is the relationship between the two coordinates of the same vectors. And this matrix here is what we call the transition matrix. So as you can see, the transition matrix, this is the notation for it. This is the indication that says that this is a transition matrix from basis B to B prime. So this is A, B, C, D, and recall that AB, okay, is actually your coordinates for vector U1 relative to B prime. Same thing here, the CD, recall from our assumptions that CD is actually the coordinate of U2 relative to B prime. That gives us a way to write the transition matrix. So the way we write transition matrix is look at the vectors in basis B, they are U1 and U2. So write U1 and U2 and write in as a coordinate vectors relative to the basis B prime. Okay, so you have vector U1 from B, vector U2 from B, but we do not put the vectors here. We'll put the coordinates of these vectors relative to B prime, relative to B prime. That's how you form your transition matrix from B to B prime. So to be clear, so suppose we have, say, a vector space of dimension 3. So these are two different bases. We don't call it B and B prime anymore, so that you can here's another example that you don't have to always stick with the notation B and B prime. So let's call the basis R, okay, and basis S. The elements, the vectors in basis R is R1, R2, R3. The coordinates, the vectors, okay, the vectors in the basis S is S1, S2, S3. So how do you form the transition matrix from basis R to S? So again, write the elements, okay, the vectors in basis R, which is R1, R2, R3, but do not write the vectors itself. You write the coordinates of that vectors relative to basis S. Okay, so R1, coordinate vectors relative to basis R. R2 coming from the basis R. Okay, do not write the vector itself. Write the coordinates of that vectors relative to basis S. And then R3 coming from here, and then write as a coordinates relative to basis S. Same thing here, if I want you to write the transition matrix from basis R to R, from basis S to R, so you take the vectors from basis S, which is called S1, S2, and S3. Do not put the vectors here, instead put the coordinates of that vectors. So coordinate with respect to what, right? Every time you talk about coordinates, it's always like with respect to what basis. So with respect to the basis R. So you have S1, S2, S3, the coordinate basis, respects to R, respects to R, with respect to R. That is how you form transition matrix. Transition matrix from R to S is going to be written this way, and S to R is going to be written this way. The reason why, as you can see from our discussion before, is because we start with this particular setup, and then we found the relationship between the coordinates of this vectors, same vectors, but with relative to different bases, B and B prime. Okay, so in the second video, we're going to look at how we apply this to a matrix, to a vector space, which consists of 2x2 matrices. Okay, so let's look at the next video, and we're going to stop right here.